All right, so last time I introduced systems of equations, and we saw that with a system of equations, the solution to the system of equations is where you have two lines intersecting. Now, the book talks a little bit about how you can graph these things and use the graph to figure out where that point of intersection is. But let's consider a situation where we have two lines that look something like this. Well, trying to read this graph, it's a bit sketchy. I don't know if this point, if it should actually be over here. Maybe my graph is just off and it should have been above that point. Or maybe it should be here. But even if it's here, I don't know exactly what that number is. Is it 175? It might be 176 or 174. Similarly, at the y-coordinate, trying to figure out what the y-coordinate is there. Is that 150 or 151 or 149? Relying on graphical methods to find solutions to a system of equation, it's not exactly the best technique. So let's think about a different way we could do this. First technique, I suppose you might call it, to solve a system of equations is called the substitution method. And the substitution method works like this. If we have our two equations, you'll notice one of these equations is written in, well, it happens to be slope-intercept form. It doesn't have to be slope-intercept form, but what we do want to use the substitution method is we want one of the equations, at least one of the equations, to read one of the variables equals something else. So one of the equations needs to be solved for a variable. So this right here, all right, so since this first equation is solved for y, that means wherever I see a y, I could replace it with negative 2x plus 10. If this statement needs to be true, then y must be the same thing as negative 2x plus 10, which means in the second equation, I can see a y right there. So that means that value right there, that negative 2x plus 10, it's going to take the place of the y in the second equation. So when I do this, I get 3x plus 5 times y, except y is now negative 2x plus 10, equals 8. You can see I still have this second equation here. This is still 3x plus 5y equals 8. But instead of writing y, I'm now writing negative 2x plus 10. Overall in this equation, you'll notice that there's only one variable now. And we know how to solve equations that have only one variable. We just simplify and move everything over to the other side. So let's just do that. Let's see what happens when we solve this. We get 3x plus 5. Well, actually I should distribute, shouldn't I? This 5 out in front of the parentheses. I need to distribute through the parentheses. So I get negative 10x plus 50. And on the other side of the equation, the 8's just sitting there by itself. I can combine like terms. That 3x and the negative 10x combine to give me a negative 7x. And when I subtract 50 from both sides, I get negative 7x equals negative 42. So I'm subtracting 50 from here and subtracting 50 from there, I get negative 42. And when I divide both sides by negative 7, this gives me x equals 6. Okay, well, what does that mean? In order for us to be talking about a solution to the system of equations, it needs to be a point. We need to have both an x and a y value. Let's see what happens if we were to take this x and see what values it gives us for the y's in these two equations. So finding y. With the first equation, if we have y equals negative 2x plus 10, that's what the first equation says. Well, if x is equal to 6, then y equals negative 2x plus 10 becomes y equals negative 2 times 6 plus 10, which is negative 12 plus 10, which is negative 2. So overall, I could say y equals negative 2. This gives me the point 6, negative 2. All right, let's see what happens when I plug it into the second equation now. 3x plus 5y equals 8. I said x is 6 though, so I get 3 times 6 plus 5y equals 8. That's 18 plus 5y equals 8. Subtract 18 from both sides, I get 5y equals negative 10. Divide both sides by 5, I get y equals negative 2. So I get the point 6, negative 2. And hey, look at that. The point 6, negative 2 is on both of the lines. So what I did is when I plugged in this value for y, what it's doing is it's saying if both of these are true, if both of these equations are true, then the x-coordinate must be equal to 6. So in order to find the point that satisfies both of these, I need to then figure out the y-coordinate. And it turns out when I do this, I could use either equation to find my y-coordinate. But since I've already solved one of the equations for y, it's a lot easier to plug it into this, in this instance, this equation. But whichever equation you've already solved for y. So in any case, you can see the point 6, -2 is the solution to the system of equations. Let's graph these two equations, and no, I'm not going to graph them. We already verified that these 2 points satisfy both equations. You can see that point 6, -2 satisfies the first equation here. Y equals -2x plus 10. That's -2 equals the question mark. -2 times 6 plus 10. I'm just checking to verify that this point satisfies the first equation. -2 question mark equals -12 plus 10. That's a true statement. And checking with the second equation, 3x plus 5y equals 8. I'm checking, my point is 6, -2. When I plug the 6 in for the x, I get 3 times 6 plus 5 times -2 equals 8. That's 18 plus -10 equals, these should be question marks. Question mark equals 8. And that's a true statement. So you can see I verified it does satisfy the system of equations. It's a little bit better to verify using algebra than it is using a graph. So that's what I'm going with.